Okay, so this is my end of year physics project. And to start with, I'm just going to show you just a little demonstration of what it does. Let's see, actually, yeah, I'll do that. 20. So as you can see, all it is a simulator. You put in different particles with different masses, charges, etc. and it just displays the result of what they do. So to start with, let's get into how this entire thing works. So I have my visual half of the project in VPython, and all it does is it just reads data from a text file and displays it in a visual format in this little window over here. And yeah, that's pretty much it on this end. Not much impressive about it. It just reads the text file, asks about what FPS you want to play it back at, and does so. And yeah, as you can see, I have the instructions right here. And most of the brunt work of my project is actually done in Java, which I can show you over here. So this is how I actually generate these kinds of the data for the simulation. So you can see here you have the driver class with their main method. So you can easily modify this to add new particles to your simulation, and you can customize where you want it to write out your data and how accurate your simulation is. The bigger this number is, the more accurate your simulation is. Basically, this number is just since it's set at, like, for example, since it's set at 1 million right now, it will multiply the force on each particle by 1/1,000,000th of a second to calculate the change of velocity, and multiply that by 1/1,000,000th of a second to calculate the change of position. So yeah, it's just kind of how much time passes in each step of the simulation. And this here is the time limit. That's the in-simulation time limit. So how much time passes in the simulation. And then right here is what frame rate you want your simulation to play back at, and what speed you want it to play back at. So right now I have it set so that it'll generate a file that'll allow it to play back at 30 FPS and half speed. So since 2.5 seconds passes in simulation time, if you play it back at 30 FPS, it'll take about 5 seconds to play. And here I just add the particles into the map and run it. So that's pretty much it for the driver class. Now, this is my second time recording, and this time I'm going to explain everything from the bottom up because I tried— oh, that's the wrong project. That's my robotics thing. Anyway, I'm going to explain everything from the bottom up because last video I tried to explain stuff from the top down and it did not turn out well. So yeah, let's start with the basic classes, shall we? Okay, column vector. So in this project I was originally using a library, JAMA, which is basically just a library for doing linear algebra, manipulating matrices and doing like finding determinants and stuff like that. And I thought I was going to use it for stuff, but I never did, so now I have just this column vector class, which is just a matrix with one column. Could have easily done it with just an array of doubles, but that's what it is now. So it has methods for, it has some constructors. I can get the magnitude of it, so that's cool. And I also have a toString method. And I can also scale it to a certain magnitude. And I also have a coordinate class, which is the same thing as a column vector. It's just saying that, oh hey, this is a three-dimensional coordinate instead of column vector. It just helps me not get as confused when I'm programming and I see column vectors inserted into arguments they're supposed to be for position. So these come with some additional methods, such as you can get the distance between the two coordinates, and that's the same thing here. And you can also get a vector pointing from one coordinate to the next. Okay, so that's your basic coordinate class. Okay. And object. Okay. So now you also have an enum of just physical constants I can use. Okay. So let's move on to the basic unit of this simulation, which is the particle. So a particle is just an object with the properties that it has a mass, it has a charge, a radius, a velocity, and a position. And also all these other properties that just are just for the program's use. But yeah. So basic constructor is that you have there, I can just read off here. So this boolean just determines whether or not the particle is static. So if it's true, the particle's motion is not affected by any other forces exerted upon it by other particles, so it just stays still throughout the whole simulation. So that's good if you want to make just like a stationary wall of, I don't know, negatively charged particles. So if you ever want to do that, you can just have a wall of particles that are negatively charged that are static. But I'm not doing that for now. And then you have a double charge, a double representing the mass, double representing the radius in meters of the particle, a column vector which represents the velocity in meters per second, and a coordinate which represents the position, the starting position. And you can see the constructor is in effect here. I've got a particle that doesn't move. Sorry, that does move. It has a charge of positive 3 coulombs, a mass of, I'm not going to even try to say that right now, a radius of 0.1 meters, and initial velocity of 0 meters per second, and initial position up 5 meters and to the right 5 meters. So these are x, y, and z coordinates. Same thing with the column vectors, they're x, y, and z components. So let's see. So the particles, they have a bunch of different properties. Where should I go next? Okay, so they also have a method called update position, which takes their current velocity and multiplies it by the time step that the map is operating on. And the map is just the class that contains all the particles in your simulation. It multiplies it by the time step, and that gives you the change in position, so it does that. And there's also a method that calculates the net force, which there's an array up here, right somewhere there, that just holds all the forces exerted on this particle from every other particle in the simulation. So it just calculates the net force by summing those up. Let's see, so can we make this window a bit bigger? Yes, we can. Okay, that's nice. There's also a method update velocity. It just uses the net force and calculates the velocity from there. And also a method for manually overriding stuff. And also a method for checking for collisions. So it just looks at its distance from every other particle and makes sure that the sum of its radius and the other particle's radius is not bigger than the distance between them, because if it is, then that means they've collided. So depending on whether or not that is, it'll either return this I, which represents the other particles, or it'll return -1, which means there's no collision. Okay, so now that we've got that out of the way, I think we've got most of the basics down, that I can actually start explaining how my whole simulation works. Let's expand on this. Oh, yeah, forgot about this. You can see I had some fun in the code. Anyway, so the map class. The map class is basically kind of the central part of my simulation. As you can see, it also has the most code, 355 lines. It's a lot. So it's kind of the class that just contains all the particles and manages the interactions between them. So let's go down and explain each and every bit. So this just constructs a new map based on if you just have a list of particles and you can put it in. And this is just an empty constructor, constructs a map without any particles. Sets time step. Yeah. Gets dimension. Oh, I also forgot to mention that column vectors, they don't specifically have to be 3-dimensional. So you can run this simulation in 2 dimensions or 4 dimensions if you wanted to. And it changes the laws of gravitation based on some assumptions I just made. So yeah, it does that. I'll show you that later. Anyway, what was I saying? I got sidetracked. Oh, right, just going through the map methods and saying what they do. This just makes sure all the particles in the map are of the same dimension, because you can't have a 2-dimensional particle interacting with a 3-dimensional particle. So that doesn't work if a particle can't move in a dimension that another particle can. This array is sticky. I'll actually explain the importance of that later. I think, yeah, these are all just constructor methods. This just adds particles to a map that has no particles yet. Okay, so this is the central part of the simulation, the run method. So this method just runs repeatedly over and over and over again. Actually, no. Sorry. I was wrong. This loop in the run method just runs repeatedly over and over and over again until the simulation is finished. So let's take a look at Map Manager 2. Where is it? There we go. Okay. That's the method we want to be looking at. So essentially, it just checks to make sure that time step is not equal to 0, because otherwise the simulation would do nothing, and that's never fun. And so while this, whatever this value is, while that's true, it'll keep doing this. So it'll calculate the forces between each particle. Actually, yeah. I actually have a description, because that's nice. And then it'll update the distance between each particle. Now each particle doesn't store the distances between itself and every other particle, but only itself and some of the other particles. So, but together I have, all of the data that I need, because the distance from particle A to the particle B is the same as the distance from particle B to the particle A, so I don't need to store that twice because that would be redundant. So, yeah. It's kind of weird since all the arrays for each particle are different sizes, but it makes things just a little bit more efficient. Anyway, so yeah. So this is my collision checker. So if it checks through each object and says, okay, if there is a collision, then basically it'll just store the result of the check for collisions from here, from the particle class, inside this variable temp, and I'll add whatever this is. And basically it says, okay, if temp is greater than I, that says, okay, there's some particle that's colliding with the particle that's being checked. And if object I is stuck to, this just checks that it's not already stuck to. Like the way my simulation handles collisions is that it sticks the two particles together and then pretends they have glue coating them, and now they're stuck together forever. So it just makes, and I just call that, I think for now, just to be clear, I'll just call it a clump. So two or more particles that have collided together is just called a clump. And it just checks that the particle it's getting stuck to is not already part of the clump. And if it's not, then it'll call this method stick particles, and it'll stick them together. And then the way my simulation handles clumps is that it actually pretends that instead of updating the individual forces on each particle within the clump, it pretends that the clump is just one particle and updates the force on the entire clump, and then the individual particles just follow the center of mass of the clump. So that's how my simulation works. So I can calculate, let's see. So yeah, I calculate the forces on the clumps, and then I update the position of the center of masses of the clumps, and then based on that, I update the position of all the objects in the clump. Which, actually, I don't know why that comma's there. Let me get rid of that. There we go. So this is just, for particles that are free, whereas this is for particles that are bound inside of a clump. And then, of course, I add one to the iteration, that way the map manager can tell how long the map has been running for. Okay, so let's get into the really nitty-gritty, now that we know the basics of how my simulation works. So here is my method that calculates the forces between every particle and every other particle. It's a lot, okay. So yeah, don't worry about this for loop stuff. That's just for how I arrange the particles in arrays. I have to do some nasty stuff. Anyway, so it calculates the force based on both the gravitational and the electromagnetic forces, and then just combines them, and then records that in the force array of the particle, which is right up here, right there. Just records the value in there from one particle to another, and then of course the other particle, due to Newton's third law, experiences an equal and opposite force, so it just takes the same force and just flips it around and says, okay, there's your force. And yeah, so it does that until every particle has whichever force has been exerted upon it by every other particle in the simulation. And then, yeah, let's look at this getForce method actually in the field class. Now, the reason I have just kind of like a class named field with the only thing inside of it is just one method getForce is I was originally going to do something else with it, like I was going to make magnetic fields, or actually this is kind of what I thought I was going to use linear algebra for, but I never did. Yeah. Anyway, so actually I really don't know what I would have used linear algebra for. I don't know. Anyway, back to the present. I was going to explain. What was I going to do? Oh, the getForce method. I was going to explain that. So there's a couple arguments in the getForce. There's mode. Actually, you know what? You can just read this. You can read. People can read. Okay. So, yeah. That's a thing. You got P and Q, the properties of each particle. You got a physical constant. You got positions. Okay, we're good. So then it just uses, well, in 3 dimensions it'll use inverse square law, and for other dimensions I just assume that gravity kind of works the same. Gravitational field just kind of works the same thing as brightness, like just from particles spreading out over space, since there's one less dimension. Like say for example in 2 dimensions, brightness decreases linearly with distance and not in an inverse square fashion, because because you have one less dimensions for the particles to spread out over. So yeah, that's hence why I've got that, which is, yeah. So that's just my assumption about fields that I made, that it's probably naive, but whatever. I don't have to deal with two-dimensional physics right now, or four-dimensional physics for that matter. I just know it works for 3. But anyway, so that's how that does that. So yeah, so let's take a look at the collider, since now we know how the basic particles work. Let's run. Okay, so we already got that. If they're within each other's radii, it just sticks them together. So let's take a look at that method. So for the stick particles method, well, first of all, it prints out that it's been stuck together and whatever. I think that was just bug fixing stuff. Yeah, so stuck to by default is -1, but if it was stuck to anything, then it would record whatever particle in here in this list it was stuck to. So this list is just an array of particles that represent the clumps. They're not actually there. So they don't actually exert forces on any other particle, but they get forces exerted upon them, and that's how the simulation figures out how the clump should move. So yeah, so it does that. Actually, what the heck? Okay, more testing stuff I should have deleted. Oops. Let me do that really quickly. There we go. Save that. And that. Okay. Anyway. What was I going to? Okay, so the way it does it is it creates a new particle at the center of mass of the two colliding particles. So it basically creates a new particle with the sum of the masses, the sum of the charge, and then also the sum of the momentum. So, and also is positioned at the center of mass of the two colliding particles. And this also works if there are two clumps coming together. It'll just combine the two particles that are representing the clumps. So yeah, it'll do that. And then here's just program stuff for making sure the particles know which clump they're supposed to follow. Yeah, and virtual relation, if you see that, like right here, it's a variable in here somewhere. Yeah, right there. That's just, I mean, that's basically an object's, a particle's position relative to the particle that represents the clump. So the way it works is the simulation applies forces to the particle representing the entire clump, and that particle moves, and then all the particles in the clump follow that central particle accordingly. So yeah, that's what that virtual relation is. It just records its position relative to the clump. And let's see. Okay. Yeah, that's the thing. And yeah, that's pretty much it for the collider. And actually, this collider caused me so many issues. I coded it all in one night, and I mean, it was good, except I made one mistake, and that one mistake, that was tiny, took me a week to fix, and it shouldn't have taken me a week to fix, but it cost me to pull my hair out. Not literally, but figuratively pull my hair out. Anyway, so So yeah, what the heck is that? Oh, that's testing stuff. That was while I was trying to bug fix. So yeah, let's take a look at the map manager. That's probably one of the last classes we need to take a look at. It's the easiest class to understand. It just manages the map, turns it on and off, tells it when to run and stop, and also, calculates what certain values should be so you don't have to do it in the driver class. Kind of makes it more user-friendly. Yeah, and also takes care of writing out the output of the program. That's also a job of the map manager. So, yeah. Let me just check to make sure I didn't miss anything. Update distances. Yeah, I already showed that. Just go away. Yeah, I don't think I missed anything. That's pretty much the entirety of my program. So yeah, I hope you enjoyed watching this, which you probably didn't because you were required to. See you later.